Hello everyone, welcome back to Introduction to Semiconductor Devices. In the course so far, we have studied the operation of PN junctions. We also looked at PIN junction and then Schottky junction. So today, we will expand our horizon a little bit. We will talk about a device which is known as MOS capacitor. A MOS capacitor is the heart of a modern MOSFET. Okay? So it is still a two-terminal device. The actual MOSFET will be four-terminal. We will talk about it after we finish with the MOS capacitor. But this two-terminal device, which is called as a MOS capacitor, gives you the necessary tools to understand the operation of a MOSFET while being simple enough. So, what is a MOS capacitor? A MOS capacitor is simply a structure consisting of three parts. Okay, so far we have looked at only P and N, or metal and semiconductor, but now we are introducing one more element in between, which is an insulator. So a MOS capacitor consists of a semiconductor. It could be a substrate of wafer. On that you have a thin layer of oxide, okay, which is an insulator, and then a metal on top. Okay. So that is why the name MOS capacitor, MOS. Okay, just a moment. MOS stands for metal oxide semiconductor. Okay. And it behaves like a capacitor. That's why it is a cap. Okay, so you're all familiar with the regular capacitors, right? So you have a two-terminal device. Let's say I have two metals. Let's say metal and metal, two metal plates separated by an insulator, right? This is an insulator whose dielectric constant could be some epsilon, right? And you apply a voltage to this. This is, let's say, you apply voltage. Let's say this is grounded, and then you apply voltage on that. Okay. So we say that this device has a capacitance which is simply going to be epsilon A by D. D is the distance. Let's say this distance, let's say, is D. Then we will say that this capacitor has a capacitance of epsilon A by D. But what does it do? Okay. It is simply a device which will, let's say if you apply a positive charge Q plus Q at a certain voltage, let's say we are adding a charge Q here, then immediately there will be a minus Q charge on the other side. Basically the capacitance is a relation between capacitance is a relation between Q and V, right? You apply a certain voltage. The device has a certain amount of capacitance, so that extent of charge will be on the plate, plus Q on one side, minus Q on the other side. This is a simple capacitor that we have studied before. So now a MOS capacitor is also similar, but it is one of the plates of a capacitor is a semiconductor instead of a metal. So you have this top plate, which is a metal, right? This is metal. And then you have a separated, insulator. This is SiO2, silicon dioxide. Okay. Right now, okay, we will change it later. It can be any insulator actually. Okay. And then the second terminal or second plate is a semiconductor. Okay. Semiconductor. So this is a MOS capacitor. That's why the name. Okay. So in this, one of the crucial parameters is the thickness of the oxide. Tox we call it. Thickness of the oxide. And the permittivity oxide, we call it as epsilon oxide. Okay. And this is essentially the heart. Okay. And to understand this, we will start with several simplifying assumptions. Okay. So we will refer to a capacitor which satisfies these assumptions as an ideal MOS capacitor. Okay. Of course, no real device is going to be ideal, but for now, to gain the basic understanding, the assumptions that an ideal MOS capacitor has to satisfy are that the metal and semiconductor, I should have put here, metal and semiconductor Fermi levels are the same. That means, let's say we have some doping. Substrate can be N-type or a P-type substrate. Let's say it has some doping. The metal also has the same Fermi level. Okay? There is no difference in the Fermi levels. Okay? Right now we will make that assumption. Okay. This is at equilibrium, okay, with no applied voltage. But if you apply voltage, of course, the Fermi levels are going to shift. as we have seen multiple times. It's not a very severe assumption. I mean, we can relax it quite easily. We will see that in the next week. And then there are no traps in the semiconductor oxide interface, or within the oxide. This is a very, very crucial assumption. It turns out that historically, one of the first transistors or semiconductors to be used was germanium. Okay, and then when they tried to grow an oxide on germanium, the interface was not very good. Okay, by which we mean, let's say you have germanium. Let's say if you take, you'll have the germanium lattice, right? Crystalline lattice of germanium, which is a perfect crystal, right? That's all. And then you try to grow germanium oxide on top of it. So this is going to be germanium, let's say oxygen, oxygen, and so on. There will be some germaniums which are germanium, oxygen, right? This is an amorphous material. Okay. And when you have this interface between crystalline and amorphous, there will be some bonds of germanium. For example, here, let's say this bond is not paired with any germanium or oxygen. It is left dangling. Okay. Or this also could be a bond, which is not satisfied. Basically, we expect that all silicon atoms are connected, right? They have this covalency, or silicon or germanium similar. Okay, they're connected to the neighboring atoms. But now it turns out that if you form this interface between crystalline and a amorphous material, there are some atoms of germanium which are not connected to any atom of oxygen or germanium. Okay, so these we call it as dangling bonds, just to indicate that they are not connected to any atom. So these are, they behave like a trap, and then they actually deteriorate the electrical properties of the device. So it turned out that even though germanium was actually one of the first semiconductors to be investigated, the interface between germanium and germanium oxide was not very good. Whereas the interface between silicon and silicon atom was extremely good. I mean, it has a very, very low defect density. Okay, we will talk about that later. So we will assume for a moment that ideal MOS capacitor has no traps, so no dangling bonds. Okay, so these are basically means no dangling bonds, which is reasonable for silicon dioxide. The number of dangling bonds is quite small, and we will study what happens if they are there later on. Okay, and also in the interface there is no charge or no trap basically. So it's very common to have some traps within the bulk of the oxide. Now, what do I mean by trap? It could be simply that a bond is not satisfied, and then there is a positively charged atom there, and then some negative charge can come and occupy it. Or sometimes a positive charge could be trapped somewhere. It cannot move because of the way the crystal is forming. So these are called as charge traps, and they actually deteriorate the performance a lot. Okay. So for now we are assuming that there are no such traps. It's a perfect oxide. Okay, which is a good assumption to make. And then the metal is thick enough to be considered as an equipotential surface. Okay, this is important because, I mean, when we take the regular, macroscopic devices, metals are quite thick. We don't have to worry. But remember, in semiconductor technology, we are always making the devices smaller and smaller and smaller, right? When we make them smaller, let's say if I make this metal 10 nanometers, I make it like this. Do you think that it will behave like a pure metal? Well, of course, no, because metal will have something called a surface scattering. The electrons which are flowing in the metal, there are no more free electrons, but they're scattering with the surface, and then the resistivity increases. Okay, because of which there is some voltage drops as the if you apply a piece of wood, you calculate the resistivity of metal as you keep decreasing the thickness. At some point, when it becomes very thin, the resistivity increases, and there is a voltage drop across the metal, and that can lead to a lot of problems. Okay, so for now we are assuming that metal is thick enough to be considered as an equipotential surface. That means if I on this metal, let's say if I apply at this point some voltage, I'm going to have the same voltage at this point. There is no difference between the voltages across. There's no voltage drop across the metal surface. Okay, and essentially it means that there is nothing like a skin depth and things like that for a metal. It's thick enough, so you don't have to worry. Okay? It's much bigger than that. That's what we mean. It's much bigger than skin depth. Okay. Anyway, and the other assumption is that semiconductor thickness is much larger than the maximum depletion region. We will look at this, And generally, this is a very valid assumption. We don't, this is not very difficult assumption to satisfy because we are dealing with semiconductor wafers which are about 500 micron thick. Okay, in the past, right now they are about 750 microns thick. That means, three-fourths of a centimeter, three-fourths of a 750 micron should be three-fourths a millimeter, three-fourths of a millimeter, right? So they're quite thick right now. So we don't have to worry about that. And oxide is a perfect insulator. Well, that is, again, we already talked about it. Okay? So it is said that the magic of silicon technology is actually the magic of the interface between silicon and silicon dioxide. Okay? So silicon dioxide and silicon interface was so great that electronic device operation has been possible. And one of the big trends in semiconductors has been what is known as gate oxide scaling. Why do I want to talk about that? Well, what happened was, we introduced this gate oxide, and if you look at the gate oxide thickness in, let's say, early 1990s, it was, 8, 9 nanometers, 10 nanometers or so, right? It's quite high. So it was a good insulator and it was a good oxide. But because we wanted to make the transistors work faster and faster, one of the requirements was that the gate oxide has to become thin. Okay? You have to make it thinner and thinner. Okay? So in a way, we are scaling. We are multiplying the gate oxide by a certain number, and then we are making it smaller and smaller and smaller. So this is what happened in the semiconductor industry over the last 30 years. Essentially, we start with some thickness of oxide, and then as you come down, the thickness was smaller. This is called 350 nanometer technology, 250 nanometer, 180 nanometer, and by the time we reached 2005 or so, we were at a point, actually 2003, I would say, we were at a point where the thickness of silicon dioxide was 1.2 nanometers. Just imagine, 1.2 nanometers is essentially maybe 5 to 6 atomic layers thick. Okay, just 5 to 6 atomic layers. It's not microns. No, we mentioned that the thickness of a human hair is a few microns, micron or so. 1,000 times smaller than that is 1 nanometer. And effectively, the capacitor we are building is actually with just 1.2 nanometers of silicon dioxide. If I don't know what else, this is magical, right? The fact that it actually worked is magical. But anyway, so this is just an image, this is what we call as scaling. We will discuss scaling later on when I discuss MOSFETs. We will discuss in greater depth what is scaling and how it improves the performance, or how it improves the speed of the MOSFET. We'll discuss it later. But for now, I just wanted to introduce, in the context of the MOS capacitor, how does this physically look like? Okay, the images you're seeing on the right side, this is what is called as a TEM image. Okay, this is called as TEM image. Okay, TEM micrograph we call it. Transmission electron micrograph. So essentially what this is showing you is we take a thin slice of the vertical cross section of a MOS capacitor and then shoot electrons at it. Okay, and most of the electrons will pass through, but wherever you have an atom, they don't pass through. So with this technique, you can actually see the way atoms are arranged in a lattice. And that is what you're seeing here. You see here, this is a silicon substrate on the bottom. And you can see this order, I'll zoom it in a little bit. So you see these atoms which are arranged. These are the bonds which are forming and the atoms are arranged. You're actually able to see these atoms. Okay? The atomic bond length will be like, 3 to 4 angstroms. And we are able to see that. This is really, magical. At least I get fascinated. It's unbelievable that we can do this. Okay, and you see this perfect lattice of silicon. On top of it, you see this is the oxide, which is an amorphous material. So you don't see that orientation, right? You don't see this perfect lattice arrangement of silicon. You see some random, silicon and oxygen atoms. And the thickness is just 1.2 nanometers. You might wonder, how did we take this image, right? And if you want to take this image, there's an equipment called TEM, which is a few tens of maybe up to $10 million or so. It's a very, very expensive equipment. With that, you can take this image. And then, so you have the silicon substrate and 1.2 nanometer oxide. And top of it, in this case, what is shown is basically instead of a metal, we are using polished silicon. So in the origin, back in 1970s and 80s, we were using aluminum as a metal. Okay. So basically, what does a MOS capacitor consist of? So you have in the metal, which is some thickness, okay, metal in this was, okay, and then silicon dioxide, and then bottom was silicon substrate. Okay. So this would be something like 500 microns thick, half a millimeter thick. Okay. Whereas this is just, in the initial days, in the early 90s, it was 10 nanometers or 8 nanometers. But by the time we came to 2003, it was already 1.2 nanometers. And this was aluminum in the beginning in the 80s. But there were certain reasons why, we shifted from aluminum to what is known as polysilicon. So the idea was that if you take polysilicon, we mentioned polysilicon in the first week of the course. It's not a perfect lattice, a perfect long range order of silicon. I mean, if you have a perfect crystal of silicon, there is long range order. You travel, 1 millimeter across the sample, and you still have the same orientation. Right? It doesn't change. But polycrystalline is that you have orientation, some lattice structure in the domains. But then if you go long distances, the domains are randomly arranged. That is called as polycrystalline. It has multiple crystals. So you have this polycrystalline silicon. And then if you dope it highly, it behaves like a metal. It's not a true metal, it's a quasi-metal, I would say. But it can work like a metal, and there was a reason why semiconductor industry chose polysilicon. Okay? So physically, the MOS capacitor is consisting of this sort of a structure. Okay? And you see, this TOX reduced. This is TOX. TOX was scaling from 10 nanometers to 1.2 nanometers. And it turned out that this was in 2003, I would say, 90 nanometer technology. By the time 2005 came, there was something known as 65 nanometer technology, where the thickness of silicon became 0.8 nanometers. These are the images taken from a presentation by Robert Shaw. He was one of the Intel fellows. I mean, Intel fellow is one of the topmost technological positions in Intel. And then he gave a presentation in 2003. I picked it up from there. You could search on the internet and you'll find it. Okay. And the picture on the left was taken from another presentation by one Gagini. He was also an Intel fellow. So you could look up that. Okay. So essentially, it's another direction. You have this lattice of crystalline lattice, and there is this 1.8 nanometer thick silicon dioxide, and then polysilicon. And you see here, you see the orientation. I mean, see this here. Silicon atoms are arranged in these lines. Here, the silicon atoms are in this direction. You have different domains of silicon. That's what we mean by polycrystalline silicon. Okay. So when the transistors became such small sizes, or when the MOS capacitors became, the thickness of the oxide became very, very small, there were problems. There were a lot of problems as such. Okay. One of the biggest problem was oxide is no longer an insulator. No longer an insulator, right? When is it an insulator? Okay, it has this band gap, but the problem is very, very thin. So electrons were tunneling above the oxide. We talked about barriers, right? And potential barriers, and across the potential barrier, the electrons can tunnel and give rise to current. So if you have a capacitor and you have a leaky oxide, oxide became leaky, I would say. If the oxide is leaking, then the transistor action will not work. The MOS capacitor will not work perfectly. Okay? This was one of the great challenges of the time. And this was solved again by Intel in 2007. And just when I was about to finish my master's, Intel announced that there is this high K metal gate, and we'll talk about that later in the week. Okay. So right now, so this is how an actual MOS capacitor looks like. Okay? And how did we achieve this silicon dioxide? Silicon, okay, I told you that you have this silicon dioxide we take and mix it with carbon, and then you can form silicon. And then you purify it, by using a very elaborate series of steps, and you get these wafers which are perfectly pure silicon crystals. So they have about 9 N purities, what we mentioned. So now, how do we form silicon dioxide? Well, it turns out that there are two processes to form silicon dioxide. One of them is called as dry oxidation, wherein I simply mix silicon and oxygen in a dry oxygen, and then I form silicon dioxide. And this is called as dry oxidation. So basically, you pass gas of oxygen and on a wafer of silicon, heat it up, and then you form silicon dioxide. There was also another process which is called as wet oxidation, wherein I use water vapor, H2O. If I pass, then I get SiO2 plus 2H2, I think. Yeah. So basically, instead of passing oxygen vapor, you pass water vapor. Okay. And this is called as wet oxidation. If you are to study the VLSI technology, they will tell you that this is the process. Gate oxidation is done by dry oxidation process. Okay. So if you just pass dry oxygen, just oxygen, no water vapor, then you will get very, very high quality oxide. Whereas if you do wet oxidation, you get low quality oxide, but you can get a very thick oxide. Dry oxidation is a very, very slow process, so you can't make a very thick oxide. But in gate, we just want 1 nanometer oxide. So dry oxidation is a perfect process for that. And using dry oxidation, we make this oxide on silicon wafer, and then you deposit metal on top of it. That's how you make a MOS capacitor. Okay. So this was a brief overview of the structure of MOS capacitor. And in the subsequent videos, we will talk about the electrical properties, how to understand the electrical properties. And so we'll meet you in the next lecture. Thank you.